Good morning, and thank you for joining us here at the Future Panther Academy. My name is Bonnie Fugiasco, and I serve as a Special Events Manager for the Alumni Association at the University of Wisconsin-Milwaukee. Welcome back to all of those who joined us last week and or the week before, and hello to all of our new viewers who are joining us today as we present the third program of our new 9-week Friday morning series called Stars Have Stories. We are presenting this program in partnership with the UWM Planetarium, where our program host, Dr. Jean Creighton, has been the director since 2007. Dr. Jean is an astronomer. Wait until you see what she has in store for you this morning. Sneak peek, it's really cool. Today's episode is called How Much Do Stars Shine? And if you are watching today's presentation live right now, you can send your questions to Dr. Jean using the chat box to the right of the video as you're watching this on YouTube. At the end of the program, Dr. Jean will answer just as many questions as she can. And don't forget, if you've missed a previous program or you'd like to find links to all of them at the website, feel free to do so. You can watch those anytime on demand. So now, if everybody gets settled in, Dr. Jean presents this week's episode called How Much Do Stars Shine?
Thank you, Bonnie. Today we get to address one of the questions from last week. How do stars shine? How do they make light? And this is a really interesting question because it tells you something really fundamental about astronomy. To understand the really big, we need to understand first the tiny. We need to understand the nature of matter and light. Think about that, just to understand this whole universe of ours. So for thousands of years, a couple thousand years, people thought that if you took a hammer to a rock and you smashed it, you started from a big rock, and then you got smaller rocks and smaller rocks and smaller rocks. Eventually, you would get to the smallest rockdom possible, and that was called an atom. And people thought, that's it, that's the smallest thing there is, okay? But about 100 years ago, we had better tools, not just a hammer, and we realized, oh, even those atoms, they're made of smaller things. And I'd like to introduce you to those really smaller things that make up everything in the universe. So these are really small. You can't see them with a microscope or not an ordinary microscope. Those are instruments that look at the really small. Telescopes look at really big, far things. Microscopes look at really small things nearby. The first thing we discovered was a proton. This is a word you may not have heard before, so I'd like you to repeat after me. Proton. We can't see a proton. It's hard to even imagine it. So I'd like you to think about a proton being a cantaloupe, being this kind of sweet melon that we're so looking forward to when summer settles in, right? That's the proton. Now, the other little particle that we found in the atom, the other little thing, if you will, is an electron. Can you say electron? Nice. We have protons and electrons. Now, the electron is a lot smaller than the proton. Think about a grape seed for the electron. Think about how small that is. And when you look at, say, the internet, or maybe some of you might have seen it in a textbook, when people talk about atoms, they put protons and electrons in this kind of pattern you'll see here, where we have circles of the proton in the middle and the electron is buzzing around the proton. But this is a very silly pattern. This is a very silly drawing, but we're forced to do it that way because we don't make big books big enough, right? We don't, the screen on your computer is just simply is not big enough. What I want you to imagine for the atom is that you took your cantaloupe and you put it right in the middle of a football field. Let's put it right smack in the middle of Lambeau Field, and your little grape seed all the way in the end zone. So basically an atom is a lot of empty space. So you and I are empty space, mostly. And the only reason why you can't take your hand and put it through your arm is because there are a lot of strong forces that just don't allow that. But otherwise, if we could see through us, there'd be a lot of just empty space. Okay, so that is an interesting idea. And you might say, okay, fine, but get me back to how stars make light. We needed to understand all that to really see why stars can make light and we can't. So what do stars do? What stars do is they can take hydrogen. By the way, the model that I showed you, just one proton, one little electron, that's what we call hydrogen, and it's the most common atom in the universe. 75% of everything in the universe is hydrogen. So if you know one atom, that's the one to know. In a star, it's super hot. So the electron is gone off. It's on vacation. It's separated from the proton. So we have a whole bunch of protons that are positively charged. And by the way, hydrogen, as I said, 75% of everything. Helium, which is, think about all those helium balloons. All those helium balloons in a party you've been to, that is a quarter of what makes the whole universe. And everything else, the carbon, the oxygen, the nitrogen, everything else that you've heard of, iron, all of it, is that itty bitty little sliver right there. Okay, so we have a whole pile of hydrogen. Now, these hydrogen protons are in fact positively charged. Okay, positively charged means that if I start bringing them together, it's like taking magnets. If I try, here I have some couple of fridge magnets. If I try and bring them together, they fight each other. They just don't want to do that, okay? The same is true of protons. If you bring them close, if they come close, they separate. They go somewhere else. But if I manage to bring them together, if I force them to come together, then I can make helium. So I have 4 little protons here. I can smash them together and I'll make the same 2 protons I had and 2 neutrons. That's a new word. Neutrons are also sometimes in the center of atoms, in the nucleus of an atom. And now I have a new atom with a whole lot of energy because the helium that I made is more energetically compact than the 4 protons I started with. Now, this is such an efficient mechanism, such an efficient way of doing things, that the sun is powered by this little operation for 10 billion years with just 3% of its mass. Think about that. You can power a star for 10 billion years with what we call fusion. Smashing things together, smashing atoms together, and making a heavier element. Now, obviously, the previous picture that I showed you is a little simplistic. What it really looks like is this. This is a picture from the inside of an atom smasher. So this is something that you would see in an atom smasher. There's several of those in the world, and I hope that one day maybe you get to work on one of them to understand the nature of the universe and the nature of atoms. Okay, well, that tells us how we make energy, how we make the energy. But I still haven't explained how come stars get to do that and say planets don't and you and I don't. Why is it that stars get to do this? All right. Now, I would like you to think about how we grow up as kids, right? We're taught when you run around, you don't bump into people. At least you try not to, right? You try and give a little bit of distance. So for example, imagine here a run where everybody is kind of running around and we're trying again to avoid. Now imagine that you were in a super crowded place, super crowded. And we gave everybody a couple of chocolates just to get them all buzzed and all full of energy. Could these people really avoid bumping into other people if they started running around? I don't think so. I don't think so. So in the case of a person, remember, we're basically empty space. If protons come close to each other, there's plenty of place for things to avoid each other. But if you're in the center of a star where it's very, very dense and the particles are moving super fast, they can't avoid it. So only in the core of stars is it hot enough and dense enough, and in a few atom smashes on Earth, that's the only place that it's dense enough for stars to slam together and make, I'm sorry, not stars, the protons in their core can slam together to make heavier elements. By the way, stars slam together too, but that's another story for another day. All right, so that tells us that stars can cook elements, and as I'll show you, this connects stars to us in a direct way. And I'm not talking about a philosophical, oh, stars are pretty and let's look at them. I'm talking truly, we are made of things that developed in stars. How does that work? Well, the cores of stars, especially if they're supermassive, like really 20 times heavier than the sun, they can cook lots of elements, not just helium. You can see here a whole list: carbon, oxygen, what you have in your lungs. We talked about iron in your blood, right? All of these elements exist in stars. Well, how does it get from the inside of a star to all over the universe? These stars blow up in what we call a supernova. Let's see a supernova explosion. Wow, how cool is that? How could I avoid? How could I avoid an explosion on this Friday morning? Now, mostly when we talk about stars, things take millions of years, billions of years. There is no video that we could possibly show that could show you that progression. But in the case of a supernova explosion, that can be real time. It can blow up in a second or less. Think about that. A star that's been kicking around for 10 million years just goes kablooey and can leave behind a neutron star, or it can leave behind a black hole. But more to the point, it spews all its guts into space. And now, when the next generation of stars comes up and the planets around that star are made, they have access to all that carbon and oxygen and nitrogen, things that are the stuff of life. Which means that quite literally, you and I are made of star dust, what we call sometimes star stuff. 90% of the mass in your body was cooked in a star, just except the hydrogen and the helium that is earlier than that. So think about it, 90% of your body came from a star. So when you look at stars tonight, and I honestly hope that you have a clear night to see stars, think of the connection that you have with those stars. As it turns out, a lot of what we talked about today, the brightness of stars, the light that they make, gave us real insight in how far stars are, and we'll talk about that next time. So I hope you can join me next time to see how do we figure out the distance of stars. And I'll be happy to take questions. I assume you have some. So the first question is, why do some stars blow up and turn into black holes when others do not? Sebastian, this is a great question, and I'm glad you caught on the fact that not all stars do this. A lot of people think, since supernova are so cool, that all stars explode. The majority of stars do not, because most stars are just too small. They don't get dense enough in their core to start smashing heavier nuclei, so they can't do it. Turns out that the stars that do blow up, some of them turn into black holes, their cores turn into black holes because they had enough mass. It comes down to when the star blows up, what's left Is it more or less than 3 times the mass of the sun? If it's more, it becomes a black hole. If it's less, it can't, it doesn't. All right.
Move on to our next question.
Yeah.
Is the sun going to become a black hole? Miley wants to know.
Miley, the sun is also too small to turn into a black hole, and maybe that's just as well. When the sun becomes what we call a red giant in about 4 billion years or so, it's going to get rid of some of its outer layers, but it's not going to blow up. It's going to be a more gradual, a calm kind of wave of material that flows off, and what's left is what's called a white dwarf. So we had white dwarfs, neutron stars, and black holes. Most stars turn into white dwarfs. Great question, Miley.
Okay, our next question comes from Sydney. How many stars exist?
Sydney, I assume you're asking about how many stars exist in the universe, right? Because if you're asking, say, for the solar system, just one, that's just the sun. If you're asking about the Milky Way, that's about couple 100 billion. So that's 2 with 11 zeros after that. If you're talking about the whole universe, then if you imagine that each galaxy in the universe is like our own, is like the Milky Way, there are about 1 trillion galaxies. Okay, so that's 12 zeros. And we're multiplying that by 200 billion for each galaxy. That is going to be, let's see here, 12 and 11 is 23. So that's going to be 2 with 23 zeros after that. The only way to really kind of approach that number is to write down 23 zeros. I think you have to do it to sort of pause for a moment to think, wow, that's a lot of stars. Hard to imagine a number that big. Great story.
That's a lot of zeros. How was the sun made? Latrell wants to know.
You know what, Latrell? I'm going to have a whole program about how you make stars. I'll just give you a brief answer to this because I'll talk about it in a little more length. The sun started from what we call the solar nebula. Nebula is a Latin term that means cloud. So you start from a nice round cloud and it's slowly spinning, but for various reasons, gravity is taking a hold in the cloud and is pulling material toward each other, which makes it attract even more material. So this cloud is going to collapse into a disk. Imagine pizza dough. You take just a blob of pizza and you start twirling it. It's going to collapse onto a disk. That material over time is going to start focusing particularly at the center of the cloud, and that's where the sun is going to form. And when that sun turns on, it blows so much radiation in the solar system that it clears out some of the material. But also in the meantime, material at the edges of the disk start pulling together and they make planets. So that's a quick answer of how the sun was made. We start, like all stars, we start from a big cloud of gas and dust. Nice question, Latrell.
What is the yellow dust looking stuff in the middle of the picture that we see of the Milky Way galaxy?
What looks like dust are stars. There are so many stars. Each of those little dots is another sun-like thing. And there's so many at the center of the galaxy, that's where it's most dense. Each of those little itty-bitty little things is a star. Nice question. Remember, the Milky Way has 200 billion stars. So looking at the center of the galaxy kind of gives you that idea. look at how many stars there are.
All right, our next question is from Lucas in Milwaukee, and he wants to know, why don't we feel the Earth spinning?
Why don't we feel the Earth spinning? There are two possible answers to this. I think the better one is the first one I'm going to give you. When you are moving together with your environment, you really don't have much of a reference to say, I'm moving. So think about being in a car. If you're in a car and you don't look outside the window and you just focus on what, say, you're holding, let's say it's a snack, or you look at your shoes, the shoes don't look like they're moving. They don't. Even though you know in your brain that the car is moving, because everything around you, the seats in the car, your seat, everything around you is moving with you. So it's very hard to tell motion unless you have a reference point. It's easier to tell that we're spinning at nighttime because we do have a reference point. We see, look, all those stars moving. And you could imagine, as we did for a long time, that the stars are actually moving. But eventually we realized, oh, those are kind of still, what makes them move is that we are spinning from west to east. The other answer, of course, you could say, but I think it's less compelling, is that we're moving pretty slowly. So it's not going to be like a merry-go-round. Woo-wee! The Earth is moving so slowly compared to the speed we would need to be tossed off the Earth that we're not feeling it at all. We would have to be spinning a lot faster for us to have any sense that we might be, tossed off the Earth like you would on a merry-go-round. Great question, Lucas. All right, well, this was great. I love the questions that you have, so keep them coming. Today, we talked about how for astronomy, we really need to understand the minuscule, the tiny, to understand the astronomical, the really big. We talked about how stars can make light by smashing protons together to cook heavier elements. And that's why we can't do that. The Earth can't do that. Most things can't do that. And that those very ingredients in the core of stars come right back to us, that we are made of those very particular elements that cook in stars. Next time, we're going to talk, as I mentioned already, about the distance to stars, and we'll see some of those stars are so far away that we started realizing, wow, we need new ways of making that amount of energy, because otherwise, how could we possibly see them so far? We'll talk about the tools that we use to figure out the distance to stars, which, by the way, is one of the hardest things to measure for us. And I super look forward to having that conversation with you next week. So take care until then. Thanks for listening.